I'd just like to welcome you all here tonight for tonight's presentation. It's been hosted by the Structures and Construction Division of Engineers Ireland. A very interesting and exciting topic which is entitled Fluid Flows for the Built Environment. We're live webcast tonight as well, which is great, and available on playback. So I'd like to welcome all those that are watching live online. This presentation by ARP will have three main presenters, which in sequence will be Dr Cristina Paduano, Dr Jennifer Keenahan, and Reamonn MacReamoinn. Just to give a brief introduction on each of the speakers for tonight's presentation, Dr Cristina Paduano is an aerospace engineer who has specialised in the field of computational fluid dynamics CFD. She's over 11 years experience in the field of numerical modelling of airflows. Cristina manages a team of CFD specialists in ARP's Dublin office, which provide a wide variety of flow analysis for buildings, including indoor thermal comfort, fire and smoke modelling, HVAC modelling, wind simulations and fluid structure interactions. Since arriving at ARP, Cristina has used the knowledge acquired from her PhD in aeroacoustics to investigate the fluid dynamic phenomena underlying the generation of airborne noise from building facade elements. With her team, she developed a numerical methodology that can predict if a facade will generate noise when exposed to wind. Our next speaker after Cristina will be Dr. Jennifer Keenahan, who's a chartered engineer and a modelling specialist in ARP's CFD team. Applications include internal thermal comfort of buildings, external pedestrian wind comfort, wind loading and pressure distribution on structures, flow of smoke and fire, aeroacoustics and tonal noise assessment of facades, and boiler emission analysis. Jennifer is a bridge design engineer involved in grillage modelling of integral concrete bridges and using Oasis GSA software, ADZEC software and Sophie Plus, the local modelling of wing walls, longitudinal and transverse deck elements, strut and tie modelling of the pier crosshead, and the detailed design of bridge elements, technical assessments reports, and design risk assessments. And then our third speaker tonight will be Reamonn MacReamoinn, a chartered engineer. Reamonn is a senior member of the ARP CFD team, undertaken 2 research masters in civil engineering at Johns Hopkins University, Baltimore, USA, and was awarded the Fulbright C/H award to undertake this master's. His research examined the fluid structure interaction between wind and bridges. Reamonn's previously worked at Ronan Donovan Consulting Engineers in Ireland, where he gained significant experience in relation to bridge design, road traffic, and traffic engineering, working on a variety of major schemes. There will be a short questions and answer session at the end of the presentation, so it would be grateful if questions could be held until the end of the presentation, please. And I'd like to welcome our webcast viewers tonight that will be able to watch online and also on playback. For our first speaker, I'd like to welcome Dr. Cristina Paduano. Thanks, Cristina.
Thank you. Thank you, everybody. So the topic of today and what we do in ARUP with my team is CFD modeling. What is CFD? CFD is computational fluid dynamics, and we are going to show how we're going to use this new technology and numerical methods to solve problems in the built and environment field. Fluid flow are quite complex and have been forgotten for many years in the civil industry. Why that? Because basically fluid flow is something that has been treated a lot in the aerospace sector, in the nuclear sector, but we didn't have years ago the capability in IT to deal with a very long simulation. So today we have this opportunity in the civil industry, and now a simulation that used to use a lot of time can be done in a couple of weeks. Plus, we didn't have the background necessarily in the civil industry to deal with fluid flow. Most of the engineers don't treat very deep fluid flow problems, don't go in the deepness of the Navier-Stokes equation, which are very complex. What we have done in ARUP is to build a team that instead is done by fluid dynamicists and can have bring those expertise that we lack in the current building and design construction sector. Fluid flow can basically, from the outside of the building till the inside of the building, can interact with our design in many ways, and most of the time they interact in a way that creates problems. So we are winding around structure. We can have fire and smoke within buildings, that is again fluid dynamics. We have HVAC system, And we can have the analysis of particular condition within particular rooms, like data center, for example. We have a different way that fluid flow can interact with the structure, for example, generating problems. And we can have also the airborne noise, so again, another unwanted problem in the civil industry. So we can have different problems created by the not understanding of fluid flow. From outdoor condition, HVAC system, natural phenomena like fire and smoke, we can have a structure interaction. All these kind of things, if not treated well and not predicted at design stage, can end up with a huge critical issue at the end when your building is built. We apply in Arup CFD to different sectors. So today, each of us, we're gonna show some of the project where we use different physics, different numerical technique, but again, all the same CFD approach to tackle problems that are regarding thermal comfort, wind, air acoustic, and also fire. I'm passing the word to Dr. Jennifer Keenahan, which is our expert in thermal comfort and the indoor microclimate.
So I suppose the first thing to consider is why we might model thermal comfort rather than using hand calculations or more conventional methods. Well, buildings by their nature and by how architecture is continually developing, they are more often having very interesting and unusual shapes and sizes and the locations of the openings. So it's not necessarily intuitive where the thermal flows, where the heat and the cool areas will be. So CFD modelling can account for this because we can import the geometry exactly from the AutoCAD model or the SketchUp model into our software, and we can model where the hot and the cold areas will be. We can look at mixed modes of ventilation if there's a mixture of natural and mechanical ventilation, lots of different extraction points and openings. We can look at HVAC assessments, the impact of the wind. We can look at facade elements, particularly brise-soleil, and how that might affect the thermal comfort inside the building. We can look at thermal losses, air tightness design, and crucially what we can do with modelling is very quickly and efficiently compare lots of different solutions. So, of course, thermal comfort of people is intuitively what we all might think, but the thermal comfort of machines is actually quite important too. A standard computer will warm up quite a bit during use. If you have a whole building full of computers, full of machines, it's going to get very hot very quickly. Typically at the moment, data centers are designed based on an energy in, energy out approach. We will know how much heat is in there, and we will know therefore how much we need to cool it down. But there's a lot of room for error. And in particular, the operating conditions in terms of temperature and humidity for data centers are quite strict as per the ASHRAE codes. And really our client wants confidence that the data center and the HVAC system that has been specified for them will perform optimally. So what we in CFD, in computational fluid dynamics, can do, we can look very specifically at the temperatures of the servers, how they heat up and cool down. We can look at whether there's a risk of stagnation points, whether there'll be a very, very hot zone and a very, very cold zone and not enough mixing. We can take a look at where the cooling units are placed and where the floor grills are placed, and ultimately optimize the cooling system for a particular design of data center. So a recent project that we were involved with was a data center based here in Dublin. There were two data halls, A and B. They were of similar size. And the functionality is, for those who are maybe not familiar with data centers, typically there's a raised floor and the cold air passes in and around the underneath of the floor and comes up to cool the computer units. And then goes back into the top of the cooling unit to be cooled down and recirculated. And that's typically how data centers are cooled down. So In this particular example, we looked at the normal mode of operation, where we had quite a number of cooling units based on the top and on the bottom of the data center. And we first of all looked at whether this would perform optimally with all cooling units in operation. But then we also took into account an emergency situation where some of the cooling units might be turned off or broken. And we found in both cases that yes, this data center would be okay, the HVAC that had been specified would perform efficiently, and there wouldn't be an overheating of the data center. As an additional piece of work in this case, we also did an external flow analysis. So there was, it was suspected that the external chiller units, which are these pink areas down here in the bottom left, were not performing efficiently. The contractor involved suggested adding some plates to the chiller units, which would separate the outflow and the inflow, as it was suspected that some of the outflow was getting sucked back in again. So we were able to add these plates to our model quite efficiently and test whether this would be a viable solution, and found that actually no, there were going to still be significant problems with the outflow being sucked back in as inflow. And so before anybody, the client or the contractor, spent any significant money on remedial works here, we were able to demonstrate that it would not be an effective solution. Another interesting project involving thermal comfort has been a hospital bedroom that we have been involved with. For this particular design, it was hoped that natural ventilation rather than mechanical ventilation could be used, and so the windows would open and close, and that would be sufficient to provide the 4 air changes per hour required to provide fresh air for the room. Of particular importance was to maintain a minimum temperature of 22 degrees Celsius. Babies are not particularly good at self-regulating their own body temperature, so it's quite important that it doesn't get too cold. In this particular case, we did an analysis of the local temperatures and found that an appropriate outdoor temperature would be about -4.5 degrees in the winter, and applied that to our model, where our model had included all of the other important elements, the heating panels, the radiant heating panels on the suspended ceiling, the various extraction points, the fans in the ensuite toilets, the louvers themselves. And we modelled all of this information and found that actually the bedrooms were not going to be warm enough. At best, they might be 17 or 18 degrees Celsius with the windows open and during the winter time. So we did have a video here that kind of captured the information. Unfortunately, whatever way we embedded it in the presentation means that I can't show it to you. But these pictures do demonstrate the realities of when we put the heating panels on a suspended ceiling and we then have openings nearby, that it's not likely we'll have a room that's sufficiently warm. So I'm now going to pass back to Cristina, who's going to talk a little bit about the fire and smoke applications that we have.
A quite well-established discipline where CFD has been the first time used in the civil industry was fire engineering. Basically, fire and smoke respond to the same law of fluid dynamics that airflow respond. So what happens is that there are some way that you can predict the production of smoke from a fire, but however you cannot really predict how this smoke will move within a building, because there are many forces that are interacting with the movement of smoke. In general, you have to take in consideration buoyancy, so the variation of density of the smoke due to the differential temperature, and also the action of pressure that can be either determined by wind, by air velocity within the building, and also by the ventilation system. So there are analytical means that has been used in the past by engineers, and this formula help us to understand how much smoke will be produced by a certain fire, depending on the fire side or on the fire load. However, these calculations are not enough. So there are a lot of prescriptive code that tell you how to use this calculation, and they tell you what to do in order to contain the smoke and fire movement within a certain area. If we use this guideline, we couldn't not have the amazing building that we have at these days, where basically you are having very big open plans. You want to have kind of artistic features, and you care about the aesthetic aspect of the building, not only its functionality and safety. The role of CFD modeling comes into fire engineering, most of it because you want to try to create something that goes outside the prescriptive codes. So in this way you have to demonstrate that your ideas, your design, even if they are not compliant, are still good enough and safe. And sometimes they are even safer than the one that you would have found by following the rules. That's why, because basically you optimize the design to the building that you are working on it. You can evaluate all the conditions within the specific area of concern, like the evacuation route, the escape indoors. And you can even assess the thermal condition within a certain compartment, for example. So you can really design system in this way that can take into account all the features of the building and implement those fire safety measurements that really utilize your building layout, and they are typically right for that particular building. I want to show you a brief project example of how CFD helped us to really cutting edge of what the code was required and go to a design limit that were quite stretched. This was a project in Qatar, an airport terminal that was having a walkway extended up to 3 kilometers. So if you have to think about going with prescriptive code, you would have to have compartmentation every so often. So you have to basically divide these 3 kilometer walkway in smaller areas, with all that concerning a lot the structure, the ventilation, the evacuation, the escaping route. So you have to add much more of what is normally required. CFD in this case was used to justify a open plan area with less evacuation route, and also with a use optimized of the ventilation system. So basically, instead of having 3 different compartments, we had 3 different smoke zone control. So basically, we had the mechanical system operating on each of these control zones, depending on if the fire was located in a specific zone. So in this case, without any separation, we virtually separate the ventilation system. We had to model that, so we have to try a fire scenario, few of them, and to verify that the condition within each of the smoke control zone were safe enough to allow the people to leave that smoke control zone where the fire was happening, and to evacuate into the next adjacent one. So this is something that CFD help us to show to the authority. How do you show that? Basically, you model your physics, in that case the fire. You demonstrate that all the important variables, for example visibility and temperature during an evacuation are very important, were kept within a certain limit. That are typically pictures that you get from a CFD analysis. So you get slices where the physics of a certain quantity is quite clear to understand. We are going to show now with Reamonn, that is our expert in wind analysis, some kind of cutting-edge project that we do also for wind assessment.
So I think it's important when we're talking about winds to just take a step back for a minute. And if we consider why wind engineering is important in terms of civil engineering. So the Meyer-Kieser building in Miami, this building failed under wind loading, And why did it fail? Well, it had no allowance. There was for wind. There was very little cross bracing in the building. It wasn't designed to take the lateral loads of the wind, and it failed. Even in the future, with the John Hancock building, where they did know about wind loading and they did take it into account, there were still panes of glass falling off the building, and it suggested that this was due to the forces of wind acting on the building. And the Citicorp building in New York is a famous example where they did actually take wind into account in the design, but they didn't design it correctly for the wind, and due to its unconventional nature, it had to be retrofit to take the wind loading. And it further back into the past, the Tay Bridge is probably the most classic example where there was no allowance for the wind loading in the design, and it ultimately led to its collapse in 1879. And we're all aware of the Tacoma Narrows Bridge, where it collapsed due to the dynamic excitation of the wind and the interaction between the bridge and the wind. But even this behaviour was found as early back as 1836 with the Brighton Chain Pier. But it wasn't until 1940 that this issue started to be tackled. And this issue was tackled using wind tunnel testing. So when we're designing for wind today, we design in accordance with the Eurocode, and the Eurocode relates to land-based structures, and it looks at buildings that are 200 metres in height and 200 metres in length. It also has a consideration for dynamic effects, and really this is just to identify occasions when your structure may suffer from dynamic effects, but essentially the Eurocode asks you or suggests that you seek the advice of a specialist. And traditionally, when you're seeking the advice of a specialist, you would go to a wind tunnel and do some wind tunnel testing, and they would advise you the best way to proceed with your design. Now, CFD gives the opportunity, an alternative opportunity or a collaborative opportunity with wind tunnel testing. Wind tunnel testing tends to be quite expensive to do. It does require, normally at the scale of large buildings and bridges, we're talking about smaller scale models, and there's difficulties in terms of similarity. There's difficulty in changing your model design quickly. CFD gives you the benefit of being able to change between different models very, very quickly. So it's more suited to an iterative design approach, and it allows you to optimize your solution. So when we talk about the structural scale, whether it's a wind tunnel test or CFD, we can use both approaches to look at the static pressure, so the forces acting on the building. We can also use it to look at the fluctuations that act on the building. And in terms of fluid structure interaction, whether it be vortex shedding, where vortexes are shed off the building, or galloping, where there's large oscillations in the building, or flutter, which was the phenomenon that took down the Tacoma Narrows Bridge. Let's just go past this ad. Let's get past it. There we go. So the Tacoma Narrows Bridge, due to flutter, started to oscillate. This phenomenon was discovered using wind tunnel testing, and really the area of wind engineering started with the Tacoma Narrows. It developed what was developed for aerospace, and they applied it to bridges, and this developed the field of wind engineering. Now with CFD and the computational power that we have, we're able to repeat a lot of the stuff that was done at wind tunnel testing. So you can also, as well as doing the wind tunnel test, you can now look at multiple different options of your bridge and optimize it. Slide. But we were considering wind actions on a structural scale, and obviously The benefit there is if you can design a structure in advance and you know that it can withstand the wind loading, that you can make savings, you can have confidence in your structure working. But there's also need to look at wind actions on a human scale. This is a video of a person up on Mount Washington. There's a 100-mile-an-hour wind, and you can see how hard this person is struggling to keep their balance. And in a minute you'll see him walking into the wind, and how powerful that kind of wind can act on a person. Now this is Mount Washington. It's the windiest place on the planet. And you're probably thinking, well, these kind of winds can't happen in an urban environment where people live. Well, they can indeed. And while you might think that an urban environment will largely shelter people from the wind, in fact, due to the configuration of the buildings, it can either disrupt the wind or it can actually make the wind, speed up the wind and increase its velocity. So this can be quite serious. In Leeds with the no, not Beaton. It's the Bridgewater Place, that's the one. In Leeds, it's a tall building. It's standing proud of the tower, of the surrounding buildings around it, and it was caused high winds to be generated on the surrounding roads. It made an environment that was very difficult for pedestrians to negotiate, and on one occasion it actually pushed over a truck and took out a pedestrian. So these are very, very serious effects, and they're worth considering at planning stage to make sure your design is safe for those around it. So one of the issues that we consider is the effect of funneling. Now, what is funneling? Funneling is the wind being forced between two buildings. So essentially it's the wind travelling down a canyon and being accelerated by the narrower space that it has to force its way through. So this is a case of a storm hitting a city in Norway. The wind is being funneled down the streets, and you can see how difficult it is for people to negotiate. Another effect is downdraft. So this is where high winds are caught by a tall building that stands above the buildings that surround it. And those high winds are directed towards the ground. So you get much higher speed winds at ground level. And this is the effect that occurred at Bridgewater Place. And you can see this woman really struggle to stay standing. She's holding on to the traffic signal there to stay balanced. And when we're talking about pedestrian comfort, we're not just talking about the forces that are acting on the pedestrian at street level, but we're also talking about the frequency that it occurs. If an event like that happens once every 100 years, you'd probably decide that it's acceptable. But if that's happening every day, it's no longer acceptable. It's also about the activity that the person's trying to undertake. If the person is looking to walk down the street, they're more tolerable of a higher wind than if you're trying to read a book and the pages are flipping in front of you. But we're not only concerned about streets, we're also concerned about public realms and squares where people habitate, and also balconies at a higher level. And not just the wind itself, but the dust and the noise that can get blown up into your face. This can make a very discomforting environment. So we were asked to do a study for the EXO building in Point Village. So the purpose of this study was to decide whether it should be granted planning permission. Wind tunnel testing had been carried out prior to this, and they had identified certain problems. We were asked to do a CFD analysis to develop to inform the design to come up with an appropriate mitigation measure. So the EXO building is 17 stories tall. It's quite tall. It's quite a bit taller than the surrounding buildings, and we identified downdraft as the major concern. So we suggested that there should be a canopy placed along the full length of the western side of the building. And then because it was easier for us to modify the model, being that we were using CFD, we were able to test this solution and show that it was a valid solution. So it was pivotal in getting planning permission. We were able to validate our CFD against the wind tunnel test, and it was possible for us to identify the appropriate solution. So using CFD, particularly in conjunction with wind tunnel testing, it can allow for efficient modelling and an iterative design process. And it was in this case was pivotal in getting the planning permission that was required. And it's very hard to put a price on that. So I'm going to hand back to Cristina for tunnel noise.
So we have seen some sort of application and cases where airflow has interacted with structure, or either internal indoor climate, or also in the form of fire and smoke. There is also something else that can be treated with the same law of aerodynamics, and again can be modeled numerically by using CFD. There are cases where airflow interact with the structure and cause the so-called airborne sound. In this case, can happen as most of the time as a detrimental issue, something that is unwanted sound, something that you don't want. Especially when we speak about building facade that are getting more artistic, and they kind of add a nice feature to a building, so sometimes they become the signature of a particular architectural firm, for example. It's important that the facade doesn't end up having problems. There have been a lot of cases anyway around the world where iconic buildings, very tall and very beautiful from the outside, they instead demonstrated to have a sound problem. And at the point that was too late to do anything other than adding a mitigation measure. I'm going to show you this video, and it's important that you hear the sound that this building emits more and less on a day-to-day basis. This is a Betan Tower, is in Manchester, and this video has been around in YouTube for a lot of time. So the people try to report what is wrong with the building, it went right. What is generating the sound is this louver that has been headed at the top of the building. It was kind of a critical problem for the architect that designed the building, because the architect himself lives at the penthouse on the top of the building, so he has to listen the resident to complain every day. Of course, the complaint, they become also, at the insurance level, etc. So become a court case, and he has to apologize and probably to pay some sort of feedback. This is something that you don't want to be famous for design a super beautiful building and then to have created this kind of problem. So there are a lot of elements in a facade that can be tricky and can generate noise. There could be screening like that, so kind of artistic holes with gaps, etc. There can be louvers with fins exposed to wind. There can be other artistic features like that. So everything that is going to be exposed to wind and has some sort of cavity or cutting edge can actually generate unwanted sound. What can we do? Basically, there was no way to predict this kind of phenomena at design stage. The only thing that most of people can do is to use existing guidance that are simply based on the fact that somehow, some people got some measurement of a building that was already built has generated noise. So what they tend to say, okay, because this building has generated noise in some part of the world, let's say that similar facade will generate noise. So tend to not to do the same design, and it's not what the architect want to do. Other ways, it's possible that sometimes you can build a prototype of the facade and test it in a wind tunnel test. But you can imagine that facades are usually a single piece, very high, very big, and not all the wind tunnel test facility can have this big enough to reproduce all the fluid dynamics. So most of the time people just try a guess, not to forget about the problem. If appear, I have to pay a lot to introduce mitigation measurement. I did a research in the past and I came out with a PhD out of my research where basically I studied this phenomena that are aeroacoustic resonance, and since I joined the ARUP team, we use the numerical method developed during my research to assess the whistling risk around the facade. Basically, what is generating the whistling is the fact that if you have a facade exposed to wind, you will have a phenomenon called vortex shedding. So, where vortices detach from the fins at a certain speed. Normally, the speed will increase, so the frequency of the vortices will increase with the wind speed increasing. But it can happen at a certain time, under certain fact that basically the frequency, instead of growing with the wind speed, remain locked. So it's fixed, it's synchronized to something else. Most of the time what is synchronized with is the frequency of a cavity that is formed by the building surface and the facade itself. So with our numerical technique, we found in which way locking can occur. In this way, we can distinguish between a design facade that is prone to generate whistling or is not prone to generate whistling. Of course, when you have to try a new numerical method, it's important that you try and you test it. So we applied the methodology for the first time years and years ago in a building in Milan. This was the type of facade that we treated, so fins with a certain cavity to the building surface. And we ran CFD model. The CFD model was meant to find the frequency of vortex shedding for each wind speed at which the facade is exposed, and to plot the frequency, so with the FFT of the frequency, we could find that some cases will show two peaks in the FFTs, which is the frequency spectra. In this case, it means that basically resonance is not happening. So the frequency of vortex shedding and the frequency of the acoustic cavity are coexisting, but they kept separated. So the cavity is not able to lock in any frequency of vortex shedding. Some other case on the same facade under different wind speed, they show instead resonance cases. So that was the lock-in. In this way, we could see by running numerical test and CFD that we can distinguish between tonal noise occurring or not around a certain design. It is important that we have shown some application of CFD, and that was only an overview of how CFD can be used in the environmental sector, in the building and construction as well. So how you get so confident in tell people that numerical method can actually be used at design stage and through all the design to advise engineers, architects, and designer which way is the best for your final goal. So the important thing is that CFD sometimes is perceived as a software that someone can learn and can go and play a few things around. In our point of view, is not like that. CFD is a methodology, a numerical technique that has to be used by expert in fluid dynamic, aerodynamic. That's why we have a team, and we try to develop further and further the knowledge in the physics. So we come back to first principle. We come back to first principle of engineering, go back in the theory, and also we kind of grow our knowledge beside that also in the IT equipment, because as I said at the beginning, years and years ago was not feasible for the civil industry to have a CFD model done. It would have taken probably 6 months of time to do a small model and with uncertain result. Today we have machinery, we have IT equipment, and a CFD model can be done in reasonable time. 1 week, 2 weeks, so it becomes more and more available for yourself as engineers, architect and designer to know if things are going to be right or wrong before you're gonna install and to deliver your project. We are all here for any question, and we would like to leave on the some view of some project that we did with using CFD, going from wind analysis, fire, acoustic, and thermal comfort. So we would thank you for the attention, and if my colleagues can join me, if you have any question, they can answer in the respective areas of interest.
Thanks very much, and a great presentation. And we'll take any questions from the floor. If anybody, great. I'll just pass you the mic so people on the web can hear.
Hi, Ger Bithell from ARP. The building in Manchester, the fins on the roof, were they purely aesthetic, or did they have some other function? And were they removed, or what was the solution?
Yeah, the solution was that it was removed, and was so much political that kind of, because a lot of companies try different ways, but then of course nobody could stand up and say I have the solution. So the solution was to remove the louver. The louver was, basically was a coverage for the plants on the roof. Aesthetical, but up to a certain point, as the functionality of coverage.
Thanks.
Questions, great.
Hey, it's Shin from ARP. I was wondering, which parameters do you get out from a typical wind tunnel testing of, for example, a bridge structure or a building?
So in terms of wind tunnel testing, it depends on what you're after. So you can get just the static force that's acting on the structure. You can get the lift coefficient and the drag coefficients. But you can also get the aerodynamic and aeroelastic coefficients. So the aeroelastic coefficients would be coefficients relating to instability such as flutter or galloping, or you can get other coefficients for the vortex shedding as well. So it depends what you're after. But in terms of what CFD can do, there's lots of papers out there showing that you can develop these coefficients using CFD. I suppose the challenge that's there for CFD is to do it consistently and reliably, and that's really where the challenge is with CFD, is to do it consistently and reliably. You can certainly mimic what's done in a wind tunnel, and then you need to define it consistently and reliably.
I was also wondering, how do you discover flutter in a bridge structure?
So there's two ways of testing for flutter in wind tunnel testing, and you can apply it to CFD in the same way. There's a free vibration approach, and there's a forced vibration approach. So with the free vibration approach, you set it going in a wind, and then you release, you deflect the deck, and then you release it, and you see how long it takes for it to stabilize. And you'll do this over and over again, increasing the wind speed, that's the impending wind speed. And then at a certain stage, it won't stabilize, it will start to destabilize. And you graph your results, and you can determine your critical velocity there. You can also do it with the force method, where you set the bridge vibrating at a certain oscillation, for a certain vibration. And again, you step up the velocity that is impinging on the bridge, and it's a similar. You look at your lift coefficients, your drag coefficients, and it's a similar. You plot your results, and again, you're looking for where it crosses an axis, and you identify your critical velocity. So it's two different ways to do the same thing.
Okay, it's Martin from Europe as well. I have two questions. First question is concerning the optimization process. How do you do it? What is the approach? Do you have some kind of an algorithm that is doing it, or you're basically building the models and trying by doing, if you know what I mean?
The dream would be to have an infinite amount of computational power that we could run thousands of models at the same time and optimize for a particular solution. Computational power is not quite there yet for that kind of optimization, but certainly we can, at the moment, we will frequently run a model, assess what the outputs are, and then use that to make an informed decision about what we might change for another model. And certainly in the case of one of the wind studies that we did recently, we had 5 iterations back and forth with the client, where they had an initial geometry. We suggested changes. They came back to us. We went back to them 5 times before ultimately the planning application was submitted to Dublin City Council. So in that case, it is an optimization approach, but not in the hardcore mathematical sense of optimization.
I guess that is important at this point to say the difference between a CFD modeller and a CFD modeller that only use the software or knows the fluid dynamics behind. Yeah. And that's, if we get a result from a CFD model the first time, that is only for us to inform our background knowledge in fluid dynamics what is going to be different if we change one of the parameters. So a person that has a background in aerodynamics and fluid dynamics can read the pressure field and understand exactly what I'm going to change to optimize in a certain point that pressure field or temperature field. A person that only uses software has to probably run 1,000 cases and not to get the solution. Is expecting the software to give the right design. So that is the difference. What we are trying to do with our knowledge in fluid dynamics is to use the CFD to inform something that is in our mind, our theory, how to move to get the goal, the final goal. So we don't need every time to run 1,000 models. That is crazy. CFD is a tool in the hands of experts in fluid dynamics to understand where to find the solution. And that can be done in maybe even 2 simulations. Or even 1 simulation, for example.
I think
if you know.
I think it's in every field of engineering like that. You can do it like by using the program 1,000 times or just analyze exactly.
But the CFD software is not intelligent as the user, So the user need to use that tool to understand. Okay, I know how fluid flow move. I know what is the parameter that by change that I will get this differently.
You also said that you're basically coming back to the theory and you're like modeling everything from the very beginning. Of course, you're using some kind of a packages, but are you just like using some kind of a MATLAB programming, or is it?
We use MATLAB. Consider that we use different CFD software and we interface this software with different mathematical tools like MATLAB. We use ParaView to post-process the result. We have our own in-house program to elaborate wind data. So our work as a CFD modeller is a lot academic and theoric. So we never forget the way to, and sometimes also we write equation by hand. The best things to understand the fluid dynamic problem is to say, okay, these are my Navier-Stokes equation. What can I forget and when I have to solve? And that is something that we have continuously beside the engineering day-to-day work. We have still keep up to date with the theory, all these kind of things. So a CFD modellers is kind of three profession. You have a fluid dynamics person, you have an IT guy that is quite smart with using the system, but you also have a mathematician, so it's kind of a mix of profession.
One last short question. What about the calibration of the models? Because of course you're modeling something on a computer, but you have to calibrate your parameters that you're using.
So most of the time, for different aspects, for example,
Depends on the application.
Depend on the application. So sometimes you have to rely and validate the result against, for example, data that you receive from papers of research. Someone has done the test somewhere in the world. For example, in fire, someone has done test about how things will burn, what kind of temperature they will generate. So you have to get this data, reproduce similar model, and calibrate the model against this data. But that is a validation of your model. Then there is an internal numerical validation that is come with the numerical mesh, has to converge, all the sort of parameters need to be solved. So that you have a kind of checklist numerical that you can do, and then you have to also kind of provide that after that the model is correctly numerical, is still valid. So it represents something quite good if you compare against reality. So you have to do different things, and Reamonn can explain that with the wind tunnel, for example, is one way that we use to validate our model in wind.
Yeah, and the wind tunnel one is an interesting one because the wind tunnel itself has its own limitations, and you're trying to reflect reality in a wind tunnel, but it doesn't quite do it itself. And then you are validating off the wind tunnel. So an interesting exercise is to take a real life structure and do it at that scale, and also in CFD, and also do it at the wind tunnel scale in CFD, and see how the results differ. So it depends on the application. In an ideal world, you'll have a perfect analytical solution that you can compare it with. In CFD, due to things like turbulence and other flow complications, you never really get a true analytical solution. So then you're trying to make it best fit, and you're trying to find where someone, like Cristina was saying, where someone has done a paper in the past and has very well documented, and then you want to get your result as close as you can to that.
Thank you very much, and thank you for the presentation.
Yeah, of course, yeah. Sure.
Hello, thanks for the presentation, it was really good. I'm just wondering, is there, like, you touched on so many different fields there, is there any other ones, like one that jumps to mind is for maritime, in terms of modelling the flow in harbours and bays, and, you know, in terms of power generation and current flow, is it used for that, do you know?
Yeah, it is an application of resolving water flow, basically. It's the same, the software are there, can be the same. The only thing that is a little bit limited at this moment is that sometimes when you look at a maritime application, you look at quite a wide domain. You look at areas of kilometers and kilometers around a certain structure. So there are software that are more basic, and they perform some rough and very coarse calculation, and most of the time they are sufficient to design a structure in the sea, for example. So sometimes CFD is not used because there are other basic calculations and are good enough. But there are probably more use, and we are entering in this field as well. So we would like to apply in the future.
Yeah, so when I was in the States in Hopkins, one of the professors there, Professor Dalrymple, his area of expertise was maritime CFD. And he's one of the most famous people in the world for this application. So I did a small study with him to do with plumes in the ocean. But he would look at sedimentation transport and interaction with harbours and various other things. And his interest is how to get very good, reliable simulations of wind effect and waves and all sorts of things. So it can be done. It's very intensive computationally. So and also you have to take into account different flow effects as well. So it's quite a complicated area. But yeah, we'd like to get into there at some stage.
Thank you. I suppose my last question, or my question is probably basic enough. It's in terms of the Eurocodes, is CFD an alternate acceptable substitution for wind tunnel testing?
Yeah, so the Eurocode allows for using wind tunnel testing and CFD. I suppose the big question is, would your local authority or your regulatory authority accept the wind tunnel analysis, or the CFD analysis? For a lot of the major span bridges, they do both wind tunnel testing and CFD. So you'll see reports for both. A lot of the expertise in terms of those bridges, in terms of the wind analysis of those bridges, is in wind tunnels. But more and more wind tunnels themselves are investigating CFD and have CFD modelers in there. So it's getting there, certainly. It's something that's growing.
So potentially in the long term, or in the short term, it could be significant savings gained from avoiding wind tunnel testing and relying on CFD modelling.
Yeah, there was an interesting bridge in Italy built recently, and they weren't expecting it to suffer from any wind effects. So it was designed in accordance with the Eurocode. And then when it was being constructed, they found it to be quite lively. And it was actually a concrete deck. It was normally it's a steel deck that you'd be expecting that behaviour from. Sure. So it was on site. They didn't have much time. So they did a CFD analysis of the deck, and they found an optimal deck cross-section to stop that behaviour. And then they took that cross-section and put it in the wind tunnel and tested that section of the wind tunnel and found that it was stable. They also tested the original cross-section and found it was unstable. And then on site they implemented that change. So yeah, no, it's coming along. It's not that far away.
That's great. I'll just take one last question, and I'll leave you guys alone. Thanks a million.
Thanks very much. It's actually a related question to the Eurocodes. So, are you of the opinion that there are actually limitations in the codes, or actually aspects of the codes that can lead you to a wrong solution? And do you see the writers of the codes actually not just taking the point about acceptance of alternative solutions, but actually mandating requirements, or even abandoning some of the clauses in codes that, to be honest, lead to incorrect solutions? Do you know, is there any movement in the Eurocodes to actually acknowledge and accept and revise those issues?
The simple answer is I don't know. But I suppose...
I think it can go both ways.
Yeah.
I think in the idea of the codes being wrong could be too conservative or not conservative enough. And that varies depending on the application that we look at. So like the fire codes, for example, are extremely conservative, and the CFD work that we're doing are demonstrating that we can be less conservative in that area. Whereas it's possible in the case of the wind loading that the loading that we apply as per Eurocode is not enough. So it can go either way in terms of being wrong. I'm not aware of any planned changes to the codes, but we can try.
I guess that more that people will apply and try to design with different approach, either than following the code, that everyone can follow the codes basically. So the design will come, let's say your goal becomes in design something new, something better, something different, in growing by doing this. So, and sometimes the challenge becomes in forgetting about the code and try to do something that is cutting edge, and cutting edge become with the risk of or a new methodology. So I guess that this is what people are moving towards. So probably the code, what is restrictive and prescriptive today, may be not there in time. That happened, for example, with fire. What was normally prescribed in the guideline for fire, then the history showed that for design in fire engineering, CFD was used, and different fire solution were used instead of the code, and then the code changed after. So now it's normal in a fire code to see you can show your solution by using CFD modeling, and I will accept it. So that CFD become part of the code, part of the rules as well. I think that wind is going to be like that very soon. Also because wind, for example, in the aerospace sector, that is a normal practice, doing a lot of CFD modeling, and you don't have code. You do a lot of CFD modeling, and then you may do the last test. You cannot waste a lot of wings of airplanes just to test and test. So you do that, and that is normal applied in a field that is where safety and design is really very important. So it's only a question of time. And
I also think the code is developed to cover 99 or 95% of all cases, and it's there to be conservative for those 99 and 95% of all cases. And where CFD operates is outside of that area, or where wind tunnel testing operates is outside of that area. There's wind load in the code is generally assumed to be horizontal. Whereas if you've got a downdraft, it's obviously, it's a vertical wind load. So I don't know. I don't know. I know it took a long time to put the Eurocode together, and I don't know if there's that much appetite for people to get together and go through that struggle again. And for the most part, the Eurocode for very conventional designs and structures seems to be adequate. So I mean, yes, I'm sure it will advance in time. But I just think for the moment and I think also in terms of CFD and the computational power, it's only going to increase. And when the margins come down and when we can do an awful lot more, a lot quicker, then you'll see people straying from the code even more because there's an opportunity for them there. So.
Thank you to the three presenters, an excellent presentation and very informative as well, and for the detailed and great responses to questions. And thanks to all the webcast viewers as well today and attendees. Thanks very much.